This lesson deals with revisiting our complex power system. You can find these notes in the ECE202 ebook in Chapter 16, starting on page 13. The power company charges customers only for the real power consumed because the reactive power, due to capacitive inductive loads, has an average value of 0. In our simple electrical power system we did on page 9, we saw that there was power lost in the wires connected between the source and the load. Since the power lost is the magnitude of the current in the wires squared times the resistance of the wires, then we could reduce the losses if we could lower the magnitude of the current. Now, most homes and factories have combinations of heaters and motors. This results in loads that have a real part and an imaginary part that looks inductive. Now, in Chapter 8, we showed that parallel resonant circuits at resonance have nearly the largest magnitudes of impedance. Now, since our loads look inductive, to be able to resonate this, we would have to add some capacitance. But adding capacitance doesn't add any real power consumption, as we'd seen in our previous video. So what's happening is that we're able to store energy locally in steady state and to swap it back and forth without sending it back down the line, where it would be dissipated by the resistance of the wires. Let's take a look at our power system example again, and let's calculate the value of C that we would need to add to resonate this load at 60 Hertz. Now let's repeat the calculations we did on pages 9 and 10 and see what the power savings are in this particular case. Okay, so we're going to add a capacitance across the load. What I need to do is to find the value of C that would produce a real part with an imaginary part that's equal to 0. So let's find the impedance of this load. So we've got R plus j omega L in series, and then that's in parallel with the capacitance. So we take the product over the sum of the two impedances. Let's multiply numerator and denominator by j omega C. Get rid of this term, so we just have R plus j omega L. Have a 1, j omega C times R, and then we'd have a j squared times omega L times omega C. So we get a j squared, which is minus 1, and then omega squared LC. Let's multiply by the complex conjugate of the denominator, and then we can create a real and imaginary part. Take this term here and take its conjugate and multiply numerator and denominator that. We're just multiplying by 1, so we got their same value of impedance. Let's calculate the real part first here. So R times this would be real, and then the j omega L times this term would also be real because we're going to get a j squared. So that j squared will give me a minus 1 with the other minus 1, and I'll have an omega squared, and then I've got an L and a C and an R. For the imaginary term, it would be this times this, that's this term, and then also this times this term, so we've got a minus j omega CR, and then R again, so you get an R squared. Let's pull out that j in front. And then the real part squared, and then the imaginary part squared, inner product terms cancel. So this has a real part and an imaginary part, where here's the real with this denominator, and here's the imaginary with that same denominator. Okay, to be in resonance, the imaginary part has to be equal to 0. So what value of C would make this happen? Let's just set that equal to 0. Just be setting the numerator equal to 0, because for the equation to go to 0 with the denominator would have to be infinite. And that's not possible. So let's take the numerator here, which is omega L times the quantity 1 minus omega squared LC, and then let's set that equal to omega CR squared. The omegas drop out, so I've got L times 1, and then I've got L times this, and I'll put that on the other side of the equation. So I've got the CR squared, and then I've got now a plus omega squared, and I've got L times L, so L squared times C. Let me take this equation and pull out a C. So I'm left with omega squared L squared, and then R squared. So now I can solve for C. It's going to be equal to L divided by omega squared L squared plus R squared. Now what's the value of L and R? Well, in our statement of the problem, we just had the value of the impedance at 60 Hertz. So let's go back and calculate the effective value of L. J omega L is equal to J times 2 pi times 60 times L, and that was equal to 2.023. So I'm going to solve for L as being 2.023 divided by 2 pi 60, and it's about 5.3662 millihenries. Now let's go stick that back in this equation. So I've got 2 pi times 60, I got the value of L, and I'm going to square that, and I'm going to add the value of the resistive part, which is equal to 3.32. I'm also going to square that. It turns out to be 355.02 microfarads. Now you can't get exactly this value of capacitance, but I'm going to use this value to show if you truly had this value, what would happen. Of course, we'll have something very similar to that when we pick the nearest value of capacitance. Let's calculate the impedance of this capacitor at 60 Hertz. So it's equal to minus j over omega C, minus j over 2 pi 60, and then 355.02 microfarads. It turned out to be minus j 7.472. Let's calculate the value of the impedance of this capacitance in parallel with the motor's series R and L. Take the product over the sum again, so here's my impedance of the capacitance, and here's my impedance of what's in parallel with that, my real and imaginary part, my inductive part here. and over the sum of these two. So here's plus this. So multiplying this out, this times this term here would give me a j squared, and I cancel the minus, and I get 15.116. Product of these two terms is minus j 24.807. Real part of 3.32, and then adding these two together, I get a minus j 5.449. Putting this into polar form, I have a magnitude a little bigger than 24 or 15, and then I have an angle that's going to be in the fourth quadrant, a little bit more negative than 45 because this is longer than this. The magnitude of this will be a little bigger than 5.4, which is 6.381, seems reasonable. And again, I'll be in the fourth quadrant with the angle being more negative than 45 because this is longer than this. But these turn out to be the same value, and so their difference is equal to 0. Effectively, my load now looks like 4.553 at angle 0. In other words, 4.553 plus J0. And of course, we expect this at resonance, that by adding that capacitance to our motor's equivalent impedance, we were able to get rid of the imaginary term. Now, this should make the current in the wires go down. Let's analyze our power system now with this capacitive load that's resonating with the inductive part of the load, and we're just left with a real part. Let's solve for the current that flows in our circuit. That's going to be the voltage 240 at angle 0 divided by the total impedance, which would be the 4.553 plus the resistance of the wires, plus the imaginary part. This has a magnitude of 4.9484, a little bit bigger than this, and the angle is still pretty close to 0 degrees because this is pretty short compared to this. So now the ratio of these two is 48.5 amps RMS at an angle of minus 1.362. So we've seen a change in the current from what we had before. It's dropped to a magnitude of 48.5. Of course, the voltage across the load is just Ohm's law, so it's the resistance times the current. And now that's 220.82 at an angle of minus 1.362. So we have more of that voltage that's coming in across the load. We start with 240, and now we've got this thing up to 220.82 in magnitude. Let's calculate the power absorbed by the load, the real part, and then the imaginary part. So here's our real power. It's going to be the magnitude of the current squared times the equivalent resistance, which is now 48.5 amps squared times 4.553. So 10.7 watt kilowatts. We actually have more power now in the load, and this represents what the motor can do in terms of work. The reactive power is the magnitude of the current times the reactance, but that's equal to 0, so the overall reactive power is 0, which would be 0 vars. Now the power that's in the lines, again, is going to be real and imaginary. So our real power is the magnitude of the current squared times the total resistance of the wires, and that's again one going to and one from the load. But now this has gone down, so our power absorbed by the wires has dropped to 926.8 watts. The reactive power is the magnitude of the current squared times the reactance, again, going and coming, the total of those two wires. That's 276.6 vars. Calculate our complex power. It's the voltage times the current coming out of the generator conjugate, which is also the load current. So we're going to change the sign on that angle from minus 1.362 to plus 1.362. Product of those two now is 11.64 K, and then the angle is the sum of the two, 1.362. Putting that into rectangular form, we have a real and imaginary part. And again, the units on complex power is volt amperes. The real part is in watts, and the imaginary part is in vars. We have shown theoretically that the power generated equals the power absorbed, but let's just check it again. So here's the power in our load, real, and the power absorbed in the wires, and that's 11.6368 kilowatts. And then our reactive power for the load was 0, and then our line was 276.6. That's exactly equal to what we calculated on the last page for the real part generated and the imaginary part. What's the power factor? It's a cosine of the angle between voltage and current, but now that's in resonance, and so it's purely real. So it's a cosine of 0, so it's a power factor of 1. So we're able to change the power factor from 0.85 lagging to 1. Okay, so what's going on in the load? Let's take a look at this. So you have a voltage across the load at a magnitude and angle, and this is the impedance of the capacitor and impedance of the inductance, and then of course the resistance. The current that's flowing in here is going to be this voltage divided by the total impedance. We'll convert this into polar form, a little bit bigger than 3.32. Going to be in the first quadrant, angle but less than 45 degrees. Now that's equal to 56.8 amps at an angle of minus 32.722. Current in the motor has gone up. Now we have a current in the capacitor. It's also going to be the voltage across it divided by the impedance of the capacitance. So let's put this into polar form. Magnitude is 7.472. Angle is minus 90. And now the ratio of this is 29.553, and the angle is the numerator minus the denominator angle. Now let's use this to calculate the real and imaginary power in our load. So the power absorbed is the current squared magnitude times R, and that's now 56.8 amps at 3.32, and that's 10.71 kilowatts. and that was what the power in the load we calculated before. The reactive power is the magnitude of the current times the reactance, and that's 56.8 squared times 2.023, and that's 6.526 kilovars. Now, the reactive power in the capacitance is equal to the magnitude of the current squared times the reactance of the capacitor, but that's a minus 7.472. Its reactive power is a negative 6.526 kilovars. So the sum of these two is equal to 0. So what's happening is we're swapping energy between these two once you reach steady state. We're not sending that energy back down the line where it can be dissipated in the resistance. Let me define the efficiency of transmission as the real power in the load over the real power generated. So we've got 10.71 kilowatts delivered to the real part of the load and 11.636 K generated. That's an efficiency of 92%. I didn't do this in the last example, but if we repeat this for the example on pages 9 to 10, which is our original complex power system, power that was absorbed by the load was 10.41 K and generated 11.64 K. And that's 89.4%. So by just adding a capacitance across the load, I was able to save the power company 309.2 watts. Power that was losing in the wires before, and now some reduction in that loss. Most customers don't really care about saving the power company energy. What the power company does is it lowers its rate for industrial customers if they'll maintain a power factor closer to 1. Usually they specify something like 0.85 lagging or higher. In this way, the power company is giving a price break to the customer to pay for that added capacitance. If you look near a factory, sometimes you'll see a large bank of capacitors, and what's happening is just this. They're adding a capacitive load to offset their inductive loads to essentially lower the current in the wires that are coming to the factory. And then by lowering their rates, they're able to pay off that capacitor in a certain amount of time. And this is a revisiting of our complex power system where we used resonance to lower the current in the wires.